In this segment, we'll be looking at some of the electrical characteristics in photovoltaic arrays. By the end of the segment, you should be able to explain current and voltage limiting behaviors in photovoltaic arrays using IV curves. You should be able to determine the total voltage, current, and power in an array of modules, and you should be able to explain the role of a bypass diode in a photovoltaic module and array. Let's start by reviewing an IV curve. Remember from the previous segment, an IV curve plots voltage V on the x-axis and current I on the y-axis. We looked at the short circuit current where the voltage is 0 and the open circuit voltage where the current is 0, which are at the two extremes of the IV curve. By connecting those two and increasing the load on the system, we eventually get to the maximum power point, which is the product of the voltage and the current at its maximum on the curve. This is the power that we would see rated on a photovoltaic module. Let's look a little bit closer at what happens to modules when they're wired together. If we make series connections, modules are connected in this positive to negative format, which increases the voltage. In this case, two identical modules wired in series would show an IV curve where the voltage increases and the current is equivalent to the current of one module. However, if we have two modules where one short circuit current is lower than the other, the modules wired in series will still have an additive voltage, but the system current will be limited to the module with the lowest short circuit current. This is the primary reason why we'd never want to wire modules together in series with different current specifications. If we did so, the power of any module with higher current would just be wasted. If we wire modules in parallel, current is additive now, and the voltage is limited to the module with the lowest open circuit voltage. If we look at two modules with identical open circuit voltages, the current will simply add on top of one another. However, if we have two modules where the open circuit voltage differs, we're going to be limited by the module that has the lower open circuit voltage. While the principle of limiting maximum power remains the same, in reality it's less relevant though, because photovoltaic modules tend to be wired in series to keep the total system current low. An IV curve can be very helpful to help us visualize how current and voltage work together to yield the power output of an array. The next thing to consider is what happens as current flows through a single module as well as through an array of modules. Recall from the first course that modules consist of numerous solar cells wired in series, so we can think of the electrical current as running throughout the whole module cell by cell by cell. This extends to each module being connected in series as well. Any single cell or module that stops producing current becomes an electron sink rather than an electron source. This might happen when a module is shaded or otherwise faulty. This interrupts the continuous movement of the electrons, which decreases the operating current of the module or the array. Let's take a look at what happens when a module wired in series undergoes some shading. We see that the current is about 3.2 amps right now. However, if I shade just one cell, we see that drops down to 1.6 to almost 1.7 amps. However, blocking even less than a quarter of that panel brings my current all the way down to less than 0.15 amps. And of course, then blocking the whole cell brings it down to 0. So this shows that when we have a shading, current can't flow through the cells. Instead, the cells become an electron sink rather than an electron source. To prevent this from happening, a circuit component called a bypass diode is installed in modules, so current is diverted around cells that act as a sink, meaning that they are taking in current versus producing it. One or two bypass diodes are typically placed in a module, creating circuit segments. If a cell in that segment stops producing current, or current that's lower than the rest of the module, electrons will be diverted, and instead of going through, they'll pass by and go through the rest of the cells and other segments in the module. The voltage will decrease according to the number of cells that are removed from that segment, but the current will not go down since the cells are wired in series. If diodes weren't used, the current would backfeed, and instead of that cell producing current, it would essentially absorb or take in that current, which could potentially overheat the whole module. For example, this module is made of 36 cells wired in series, 18 on one side and 18 on the other. They're electrically separated in the middle, and there's a break here. That break is where we would find the bypass diode that electrically separates the two sides. If one side of the module would go down, then the other side would be working. The downside to any bypass diode is that it lowers the operating voltage slightly, usually less than 1 volt. This small decrease, however, prevents the current and power loss that would occur. This more than makes up for the missing voltage. Bypass diodes are put in by the module manufacturers and are not typically serviceable. Likewise, if we have one module that is non-functional or has a lower output than the other modules in a series string, we can put in a blocking diode. A blocking diode in an array is essentially the same as a bypass diode within a module and prevents backfeeding from other modules or sources like battery systems. Backfeeding from a battery would occur when the battery is at a higher voltage than the module during, say, non-operational times, like at night. One can think of a bypass diode as a one-way valve that only allows electrons to flow out of the module but not back in. This increases the overall energy output, reliability, and safety of a photovoltaic module. In the next module, we will determine how to size photovoltaic systems under real operating conditions.